So this is the last in a series of video-based lessons that will introduce the basic data warehouse implementation in general and ETL process in particular. We will discuss each of the ETL steps in some detail, including some implementation-related challenges such as slowly changing dimensions. We will conclude with a brief discussion on Microsoft's SQL Server ecosystem as it relates to data warehousing and business intelligence. As with the transactional processing systems, the implementation stage begins with the conversion of the dimensional model's ERD into an initial set of create table statements. Each of the dimensions will get an auto-generated surrogate keys, SKs, created during the ETL process, and the fact table is populated with those surrogate keys corresponding to each dimension and based on the clearly defined fact table grain at which the measurement are kept. In addition to the translation of the dimensional model into RDBMS, such as SQL Server, most of the effort regarding data warehouse implementation is the careful design and implementation of the ETL process. So when we discuss DW implementation, we are mostly referring to the implementation after design of the ETL system. As was discussed in the intro to DWBI, the ETL process is also known as data staging, sitting between the operational source data and warehouse data storage. See slide 19 in the intro DWI presentation. ETL process is the key bridge between the operational and analytical worlds. Without it, DW is deprived of not only its raw material, which is the data, but also of the transformations of the many data elements from operationally efficient codes to business user-friendly descriptions, which, when adequately summarized and presented, can help drive strategic decision-making. So, in a nutshell, ETL is a process of extracting the data from multiple operational sources, cleaning and transforming it into a more user-friendly form, and then loading the data into the data warehouse. As we already mentioned in the intro to DWBI, ETL process is very detailed and time-consuming, often eating up to 75% of the data warehouse implementation budget and time. Initial extractions should include all the possibly relevant data sources, not just operational databases, but other internal as well as external sources of data. Design of the extraction procedures, as well as cleaning procedures and transformation functions, is the most difficult aspect of the ETL process design. Efficient extraction followed by the right transformations will make DW data easier to understand and interpret by the business users. Finally, the loading, especially of the huge data sets, needs to be done at most opportune off-peak times, typically by night. This slide provides a visual schematic of our ETL process of extracting and integrating operational data from multiple OLTP sources or source systems, shown here on the left, into multiple staging areas where it's cleaned and transformed into a more palatable form, further integrated into an operational data source, and then loaded into actual data warehouse storage for use by the business users in their BI applications. Operational data extraction design is not a trivial matter. Every piece of data has to be, first and foremost, thoroughly understood and carefully analyzed. The metadata should document everything that is possibly relevant about a particular piece of data. The source or sources, data type, range of values, coding, decoding schemes, numerical precision, etc., etc. One of the critical aspects of this analysis is determining if the data in the operational systems has only current values, or is there history associated with the data. It is because of the information hidden in this historical data perspectives that we often need to revise parts of the dimensional model that will otherwise be able to represent only the original, quote-unquote, or just the current values, but not both or anything in between. In terms of data capture, in copying of the data to initial staging areas, we need to be able to differentiate between the static and dynamic data capture. Static data capture typically refers to the initial data load, although at times it can represent full extraction at a later date when a particular table is completely refreshed. As such, the static data capture extracts the operational data as of a given point in time, and if there is any history in the data, it will be extracted as well. Dynamic data capture typically refers to extractions that happen after the initial warehouse load. These extractions are incremental in nature. Only the data that changed during a specified time interval is retrieved. This does not just mean the fact measures that change frequently, but also changes in the dimensional table data since the last extract. Not all of the operational data source systems support dynamic data capture. The part of the design that is conceptually, if not implementation-wise, the easiest is when the operational data comes from RDBMSs with the capabilities to track data changes through triggers or log files. Operational data coming from flat files typically does not have these capabilities unless a conscious effort is made to program them into these source applications. Another point of data extract distinction is the real-time, online or immediate, or deferred or offline data capture. Again, the capabilities of the operational systems are the key. Using database triggers and log files, we can program the immediate extraction of data as it changes from the previous state. With other source applications using flat files, the programming effort to accomplish the same is likely to be much more substantial, both initially and later on. Deferred extraction relies on time stamping and comparison of subsequent extracts to locate and update data changes. The downside is that any changes that happen between the two extracts is lost. On the other hand, offline extracts are much less taxing on the operational systems when compared to the online extract, so that is an additional consideration we need to be mindful of. Finally, in terms of extraction tools, the organizations strive for a balance between the in-house applications and third-party tools. Both are expensive in different ways, with in-house tools preferable when the business processes captured by operational systems do not change much or often. Third-party tools, listed towards the middle and bottom of the slide, are better suited for situations where operational systems changed often and substantially so. This is because they are much more flexible, since they need to be generic and adaptable to a variety of situations, and also have much better metadata management capabilities. This is a good place to stop.